Hi, welcome back to My Smart Learning. This is a physics and science lesson for my Year 9 class in particular, but it's GCSEs, so it's useful for Year 9, Year 10 and 11. However, it's stuff that the Year 7s have done as well, so it's useful for Year 7 too. So keep watching our videos on My Smart Learning, you'll get all the different science lessons that you want to go through. Now, what we're focusing on today is energy transfer by conduction. We'll focus on conduction, but I'm going to quickly, briefly go over convection as well. Although it's not in this part of the syllabus, it's useful to know about convection too. So we're looking at the energy transfer or thermal energy. Remember, thermal energy store, and as it transfers, we call that a heating effect. So one type is conduction and the other one is convection. So that's what we're focusing on today. So how do materials conduct is our learning objective. But before we start, we always have our virtual high five. So recall quiz, get all 5 correct and you'll get a virtual high five from me. You can't buy those in the shops. So number 1, these are the equations that we did from our energy topic. We're partway through this now. We're in sort of chapter 2 from the physics caboodle textbook. We've done chapter 1, which is all about energy. Chapter 2 is all about thermal energy stores and transfers. So what's the formula for work done is question 1. Question 2, GPE equals, number 3, KE equals, number 4, what does efficiency equal? And number 5, power equals something. Okay, pause the video, have a go at answering those questions, and if you're ready, you can unpause now and we'll go through the answers. Right, so work done is force times distance, or W equals F times S. Remember, we use the letter S for distance, not D. GPE equals mgh. If you remember from last time, GPE equals mgh, mass times gravity times the height, gravitational field strength. Question 3, KE equals half mv squared, half times mass times the velocity, which is the speed, squared. Efficiency is equal to the useful energy input divided by the total energy. Okay, so the useful energy that you get out of it, so the output, the useful energy over the total energy input times 100%. And power is the energy divided by the time taken, so E over T, or the PET equation, P over T, P equals E over T. So energy is equal to power times time, and power is equal to energy divided by time. So, first of all, keywords then. This is the things that we're going to be focusing over this lesson. And the next lesson, heat transfer, we'll look at conduction, we're going to look at insulation, reducing thermal energy transfer, we're going to look at convection, and we're going to look at radiation. We'll focus on radiation next lesson. So, 3 methods of heat transfer then. We've got conduction, convection, what we're going to look at today. We got radiation, which is the next lesson, which you'll have on the Friday's lesson, and we could also look at some kind of insulation. Now, conduction then. What is conduction? Well, just before this lesson, I was heating up some water in a pot. In the pot, the metal pan got very, very hot. Well, how did it get hot? The metal solids conduct. Okay, so conduction only happens in solids. It cannot happen in fluids. The water's got hot because the metal pot has got hot because of the heating effect from the gas fire underneath, or if it's an electric cooker, it would be the electric conductor underneath. So the metals are good conductor. So the heat energy conducts along the handle, and then eventually, if it's a metal handle, it will burn your hands. So obviously you don't want a metal handle, you want a handle that's an insulator, so it doesn't transfer the heat energy. So you'd rather have something like plastic or wood, because that will prevent the heat from transferring. If it was a metal handle, eventually it'll get hot because metals are good conductors. And we're going to look at the reason behind that in a second. Convection then is where hot, it only happens in fluids. Fluids because they can flow. Now fluids are liquids and gases. So gases can flow to the top, liquids can flow as well, around and round. So hot liquids rise, cold liquids sink. Same thing with the gases, hot gases rise, cold gases will sink, and we'll come back to that in a minute. And it's to do with the density. Density becomes lower as the molecules gain more energy, they spread further apart, so therefore they have a lower mass per given volume, so they become lighter, so they rise. So it will rise up. Radiation, any object that has thermal energy store will radiate heat out. Now we will look at this in our next lesson. Anything that's above absolute zero. Now what it means by absolute zero is the lowest temperature you can get in the entire universe is like minus 273 point something or other. Very, 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 very cold. That is absolute zero. Okay, so we call it 0 Kelvin because that's another temperature scale, or if it was using degrees Celsius, it'd be minus 273 or so. So at that point, all atoms stop moving, and if they stop moving, they've got no energy in the molecules, no internal energy, so therefore they can't be giving out any radiation, radiation in the form of a heating effect. So everything else though will. So everything will have, so even me right now will be giving out some radiation, and the TV as well. So what's the difference though between heat and temperature? If you pause the video, you can have a quick go at answering this question. The words are at the bottom, so have a quick pause, see if you can write that out onto some paper or into your exercise book. And if you've done, we'll go through the answers now. This is sort of talking to us the difference between heat and temperature. Heat and temperature are not the same thing. Heat is a form of energy, it's measured in joules, or we use the word thermal energy store. Heating in its sense is the transfer of that thermal energy. It goes from one place to another place, either via conduction, convection or radiation. Temperature though is how hot something is, and we measure that in degrees Celsius. So it's more to do with the kinetic energy of those molecules, the internal energy of the substance and how fast they're moving. The higher the temperature, the faster the kinetic energy of those molecules, and they move around faster. But that's due to the internal energy stores of that material, of that substance. But heat itself is the actual energy, or the thermal energy store. So heat is a type of energy that will flow from a warm area to a cold area. For example, so heat always moves from a warm area, from where it's warmer to where it's colder. So next time you leave the door open and your mum or dad shouts at you, shut that door, you're letting the cold in, you can say, sorry papa, or sorry mama, whatever you call your mum and dad. It's the heat that is escaping out of the door, not the cold coming in, because heat is the thing that transfers, or the thermal energy is what's transferring out. Cold isn't coming in, so it's a waste of energy because you've spent money warming your house up and all you're doing is you're letting it straight out the door or straight out the window. Okay, so this cup of coffee will cool down because it is giving out heat energy to the surroundings. What about this one? It's a soda, what they like to call it in America. This drink taken out of the fridge will warm up because it is taking in heat energy from the surroundings. Okay, so it will warm up. So, conduction then. Here's a quick snapshot. You can write this down as well. The words are at the bottom here. Have a go at answering those questions. Press pause, write them out into your book. I am going to post it on Show My Homework, so you get a chance to write it down in your book from that, if you don't want to press pause and do it from your computer screen or your mobile phone screen because it's too small. Okay, if you press pause, have a go, and then if you've unpaused it, we'll go through the answers now. So conduction is all about when heat is transferred through a solid, the heat is passed on by vibrations in the molecules. These vibrations get bigger when the solid has more energy, that is when it is being heated. And then the next one, we've got metals are better conductors than non-metals because the heat is carried by free electrons that can carry the energy around the metal and give it to other electrons and ions. So we're going to go into the explanations behind that. Now, one way you can investigate the conductivity of different materials, which basically means how good they are at conducting, is when you're doing a full investigation, obviously you need some kind of introduction, you need an aim for it, you need a prediction, what do you think is going to happen, you need a plan, we need the results, and then analysis of the results with the conclusion, and then an evaluation. Now in the analysis, there could be a bar chart or a graph, line graph or something like that. So if I want to measure what factors affect the rate of conduction in metals, Well, I can use some metal bars. Now, if I want to make it a valid comparison, now remember we don't use the word fair test anymore. Okay, that's old sort of Key Stage 2 language from the old science SAT stuff from a long time ago. We've stopped using that now. We don't use the word fair test. We say valid comparison. Valid comparison allows us to get accurate results. So if I'm going to be comparing different metal bars or rods, and I want to see which metal is the best conductor, which one's got the highest conductivity, as in which one conducts the fastest at the fastest rate, then my bars would have to have the same width. They'd have to have the same length. What am I changing? Remember, you've got independent variable, dependent variable, and you've got the control variables. So the independent variable is the thing that you are changing. So here I'm going to change the type of metal. So I'm going to have like 4 different rods. The dependent variable might be, I might stick some pins on it, like you see on the next slide, and I'm going to time how long it takes for the pins to drop. Now I know I've done this with my Year 7 class. We did this a couple of months back, so it's that practical. So that's the dependent variable, what you're going to measure. The control variables are everything you're going to keep the same in the practical so that you get a valid comparison. Remember we use that word, to get valid results, we get valid data, to get a valid comparison. So when you compare one metal with the other, they need to be the same. So same width, same length, we need to have the same, when they're being heated, they're heated from the same point. Okay, so they get heated by the same amount of temperature, the same temperature. The shininess of the metals. So it could look something like this. This is the practical we did. We did it with the ring, and in the ring there was 4 bars coming off that ring, and we heated it from the center, so they're all being heated from the same point. And we put some drawing pins. We put some Vaseline at the end of the 4 rods that we had, and we put a drawing pin at the end of the Vaseline. And you have to make sure that the control variable is that they had the same amount of Vaseline, because to make it a valid comparison, because if one had too much more Vaseline than the other side, what can happen is it took longer to melt on one side compared to the other. So you heat it, and the heat energy transfers to these rods, and then the wax melts, and then the pin drops, and you stop the stopwatch. Okay, so that's an investigation to measure conductivity. Okay, so conductivity is the rate at which a material will conduct. Now, how does that work? Well, there's my metal bar. Why does conduction happen? So if I heat it up, like you can see, as I give it more heat energy, so you can see the Bunsen burner going, what's happening to the atoms? They start to vibrate more and more and more and more. Okay, so in a non-metal though, so this is graphite in carbon, it doesn't conduct very well. Okay, but what about if it was a metal rod? So that's my graphite. So it starts to heat and starts to vibrate, and then the atoms along start to vibrate, and then it passes on the energy. So that's a fairly good conductor. Now usually non-metals are poor conductors, so we call them insulators. Graphite is a funny one because it sometimes behaves a little bit like a metal and a little bit like a non-metal. So it conducts a little bit, but compared to metals, it will conduct much faster. But you've got the idea that the atoms start to vibrate more. So if I heat up a metal bar, what will happen if I heat it from one end, the atoms start to vibrate, and as they vibrate, they pass on the energy to the next atom, to the next atom, to the next atom, to the next atom, and they pass on that thermal energy. Okay, it transfers through that material. Now metals are the best conductors, but some metals are better conductors than others, and that's how we test it with those rods, looking at conductivity. So for instance, copper and aluminium would be better conductors than steel, for instance. So conduction happens because the atoms gain more energy, they get more internal energy, and as they vibrate more about the fixed point, they pass on that energy to the corresponding or the next atom next to it, and so on and so on. Now metals also, when you look at the structure of metals, they have delocalized electrons, which means there's electrons that are with the atoms that don't stay with that particular atom, and they move from atom to atom, and they can transfer, the sea of delocalized electrons, they can transfer that heat along. Okay, so there's your sea of delocalized electrons. In metals, the outer shell have these delocalized or sea of delocalized electrons, and they can jump from atom to atom. And if you warm metals up, these sea of electrons will start to move in a certain direction and transfer that energy all the way across. So, two reasons you need to know why metals are good conductors of electricity. They can vibrate about their fixed point and transfer that energy very easily, okay, because they're good conductors, and pass that energy along. But also metals have the sea of delocalized electrons that pass the energy from one end to the other. Okay, so what's the reason behind the conductions? Like we just said, metals are good conductors because they have a sea of what we call these free to move delocalized electrons. They gain this kinetic energy and they can transfer it along. Whereas non-metals are poor conductors because they don't have these sea of free delocalized electrons, so they don't pass it on. So we call them poor conductors or insulators. Okay. Now, what insulators then? Most methods of insulation rely on four things. They need to be non-metals. They need to either be liquids or gases. They need to conduct, they can't conduct across a vacuum as well, so if there's complete dead empty space, there's no particles at all. Or by trapping bubbles, air bubbles or pockets, again that's just a gas, and that will stop conduction going across. So you either want a non-metal material like wool, okay, or cotton or foam or something like that, that would be a good insulator. Liquids and gas are good insulators because they're not solids, because solids conduct. And also if you've got a vacuum where there's no particles at all, or you've got like bubble wrap, that type of stuff, that will have air trapped in the gaps and therefore they will act as good insulators. So like a woolly jumper will have lots of gaps in there and make it a good insulator. So you want to stop conductivity from your house and going out of the house, because you're spending all that money on your electric and gas bills to keep your house warm in the winter. You don't want the energy from inside going out. So we're going to focus on this in one of the later lessons in chapter 2 in the physics book. You'll see it talks about homes and how homes are designed. But part of the end of this first lesson in topic 2, it does talk about, if you look in the Caboodle book, it talks about insulation and cavity wall insulation. And it's all about reducing conductivity across. Okay, so the way you want to do that, you don't want the heat to escape through the bricks. So you either want to have a gap of air between there, because remember air is a poor conductor, it's a good insulator. Another thing you can do is you can pack that space with cavity wall insulation. Another thing you can do is a double glazing, like we said. In the space between the glass will be dead air, or it would be a vacuum, and that again will stop conduction going across. But we're going to focus more on these in a later lesson. You can pack the gap between your walls with a foam. That's called cavity wall insulation. Okay, and again that's going to prevent the heat from escaping, and that's similar to like loft insulation, the fiberglass that you put in the loft, the yellow fluffy stuff. Again, that prevents heat loss, acting as an insulation, the cavity wall insulation there, and then there's loft insulation. Now, convection current, I'm going to go really quickly through convection current because it's not actually in chapter 2.1, but because the next lesson we're going to look at is radiation, then convection's kind of lost in between the two, because whenever we learn about heat transfer in physics, we always talk about conduction, convection, and radiation. So we've just talked about conduction. Now we're going to look at convection, and we'll go really quickly through it because it's not something you need to know in too much detail for this particular chapter. Convection happens in fluids. It has to be in a liquid or a gas, and it happens because when you heat them, the particles gain more energy and they move further apart. And when they move further apart, they become lighter because they become less dense. Now, density is to do with how heavy something is for its size. Now, we'll do that in a few lessons time, calculating density. But ultimately, when it spreads out, it gets lighter, and therefore lighter things rise. So hot liquids will rise, it goes to the top, the cold liquid there will sink, and you'll eventually get this circular motion called a convection current. Now in lesson, we'll do this, we'll do the practical. I'll put a little purple crystal at the bottom of the water, I'll heat it with a candle, and you'll see a bit like a lava lamp. You'll see that the purple dye rises and it goes round and round in a circle, showing you the convection current. So it looks something like this. You heat it, there's your purple potassium permanganate. You don't need to know what the name of it is, it's just a purple crystal. You add it to the water, it starts to dissolve, and as I heat it, you'll see it starts to expand because it's getting warmer, it gets lighter, so it starts to rise, and then the purple dye just keeps moving round and round. So you can see it's starting to shrink, and then it will get more dense and then sink. Now it's not the purple crystal that moves, but you'll see the dye, okay, because it's dissolved, it will start to move, and eventually that water will become completely purple because you get these convection currents. And it's the same thing in my living room here. Obviously radiator's not on now because it's been like the hottest April on record or something, or the sunniest April on record. But if it was winter, what would happen is the cold air would go near the radiator will warm up that cold air will become warm, it will start to rise, it'll go across to the ceiling, move across the room, and then sink on the colder side, and eventually you'll get this circular motion of the air, and eventually the whole room will warm up. So the warmest air actually at the beginning is at the top of the room. Eventually the whole room will fill up with warm air. So that's why having houses with very high ceilings, like here, it's very energy inefficient, because by the time your room gets warm, you have to fill up half of the room at the top with warm air before the bottom gets warm. Okay, so it's kind of a waste of energy up there because there's nobody standing by the ceiling. Right, you can pause the video, have a go at filling that in, see if you can get the answers, and if you've done that, if you unpaused it, I'll go through it now. The words are at the bottom: expands, radiators, dense, heated, current, and float. Convection is all about when a gas or liquid, which is a fluid, because it can move, moves and carries heat with it. When the fluid is heated, it expands. There we go, it expands. This means that it will become less dense, there you go, less dense than the colder fluid around it. Because of this, the warmer fluid will try to float, it will try to rise, it will try to float over the colder fluid, and this is why the warm air rises. This is called a convection current. This is how heat reaches us from the radiators in this room. Okay, so in conduction, the heat was passed on by vibrations in a solid, remember? So our focus today is about conduction, and it's all about the conduction to a solid. Convection, however, happens when the heat is passed on in fluids, by fluids expanding, rising, and taking the heat with it, so taking it round and round and round. And it only happens in fluids, which is gases and liquids. So, convection works by this then, hot air balloons as well, because how does a hot air balloon rise? Again, the fire there will heat up the air, the hot air then will rise, so it will become less dense, warm air inside of there, cold air will come out because the warm air inside of there, it's lighter and less dense than the cold air surrounding it, the hot air balloon will rise. Fridges work in the opposite direction then. So if you've got a cooler there, that means cold air will sink and then warm air will rise. So eventually you'll get a circular motion. Therefore, this cooler box at the top, this ice box here, will actually be having a cooling effect at the rest of the fridge, keeping the rest of the fridge quite cold. Okay? So it causes a convection current. So if you've got any warm air there, the warm air will rise, the warm air will cool down over there and then sink back down. But you'll get this current of air going round, and you'll have a cooling effect, keeping your stuff in your fridge cold. Another example of convection then is that you can see it spinning around. Wind is a convection current, because at the sea, where the sun is, the sun will warm up the air will rise, warm air rises, cold air will sink to take its place, and as it takes its place, that is wind. And when you get thunderstorms or cyclones or hurricanes or whatever, it's when it becomes really violent, when you get this motion happening very, very fast. Okay, so weather systems. So using that wind then, you can become a bird, because you can see, or this pterodactyl, I was going to pterodactyl, but they can fly. Obviously they don't exist anymore, but birds, you sometimes see them just sort of hovering at the seaside, because there's a convection current, and they're just literally just riding that wave of wind, right? So same thing for a kite. You hold up a kite. If you're hang gliding, you see the hang gliders, they run off the cliff edge and they go woof, they go straight up, because it's the wind that comes and catches it off the cliffs and goes straight up. And where's that wind coming from? It's coming from the sea, because the sun is warming up that air, the warm air is rising, the cold air is sinking, and it's taking its place, and it causes that wind. Okay, so to finish off, I put some exam questions and some key points on the PowerPoint. You can have a go at that, Year 9s, because that's your lesson this week, for this Wednesday. There's the exam style questions there. There's the key points. Have a go at those. Use your Caboodle online textbook. That's where the questions were from. So use those. If there's any issues, please send me a message through Show My Homework, or you can do it through the YouTube channel. Hope that's been useful and you've learned something about conduction and convection today. Next lesson, we're going to go on to radiation. I hope you got all 5 of those formulae correct, because I'm going to ask you next time again the same ones, I think, as your recall quiz. High five. If you got all 5 correct, you're going to get a virtual high five from me. Remember, you can't buy those in the shop. Hope you're all staying safe, and I'll see you guys next time. Virtual high five from me.